In the previous video, we developed what is called the weak form of the PDE, and we also saw how can we write this weak form in a abstract notation. Now, in this video, we are going to solve a very simple problem by converting first our ODE into a weighted residual statement, and then we convert this weighted residual statement into the weak form, and then we'll be substituting the approximate solution in that weak form, and we'll try to solve for the dependent variable u. Okay, so let's start with the abstract form of the weak form. Okay, now this is the abstract form that we derived in the previous video, and note that there is no approximation in this statement. This is simply another way of saying the differential equation, the governing equations of a specific problem, specifically the linear problems. Okay, now we put the approximation here, okay, u here and v as psi i's. Okay, so this is one equation, we convert it into n equations. Okay, so this is what we have now, and we take the summation outside. But here we are using the bilinear property of this bilinear operator A. Okay, so we can take the summation outside, and this, note that these brackets are not the inner product. This is some function. This is A, some operator acting on these two functions u and v. Okay, this is not the inner product, so don't confuse it with the inner product. Okay, anything with A before it, we'll assume that it is the bilinear operator A. Okay, now we take the Cj out of A, because it's a constant. These are constant value, again using the bilinear property of the A. Now we can now convert this into a set of linear system, which is Aij Cj summation is basically is equals to Bi. Okay, now if AU comma V is symmetric, since A is derived from this A, capital A matrix is derived from the bilinear operator A. If AU comma V is symmetric, if it is symmetric, then Aij is also symmetric. Okay, this is a fact. Simply if this thing is symmetric, because Ij psi I, now in this case it is symmetric, so it doesn't matter if you change I and j, you'll get the symmetric Aij matrix. You can expand and see how does this thing happen, but it's very easy to see this. Okay, now let us take example 5 of solving this ODE. Okay, so this is basically a governing equation of 1D bar problem. Okay, and it's defined in this domain, and we have specified Dirichlet boundary condition at u equal to 0 and some kind of Neumann boundary condition, because we have also multiplied a factor e here. At x equals to 2 is 10. Okay, so e u dash at x equals to 10 is 2. So we have a Dirichlet and a Neumann boundary condition. Both are non-homogeneous boundary conditions. Now, so let us write this differential equation in this form. It's easy to handle using this, and the operator Lu can be written as this. Note that this operator is different from that's in the weak form. This just we are representing the differential equation using this. We should have called it something else. Let's call him L dash u. Okay, now the weighted residual statement would be this: r comma v is 0, the inner product of r with v, where v lies in the space capital V, and we substitute the value of r here and distribute v over each of the terms. We get this statement. This is what we have been solving till this point. Now let us integrate by part, okay, to get to the weak form. So we have integrated this thing by parts, so we get this term where we have reduced the differentiability u double dash. In this term you will get u double dash, so we have reduced this to u dash, and we get a boundary term where we can put in these Neumann boundary conditions. Okay, now since Dirichlet boundary condition is at x equal to 0, so all the basis, that's why all the basis function would be 0 at x equals to 0. That's why v should be 0. Okay, we actually represent all the basis functions because this is a single statement. So in that sense, the v will be 0 at x equal to 0. So we can eliminate this term, and we just need to evaluate this expression at x equals to 2, which we'll do with the help of the Neumann boundary condition at x equals to 2. Okay, so a, considering a is also a function of x, so we evaluate a at L, e at L. L is equals to 2 here in this case. Okay, L is 2. Now, and the v at L, and we can write this EU dash part. This EU dash part is 10. Okay, so that's why we have written this 10, and a is here and v is here. So we have substituted the Neumann boundary condition here. So this is the power of weak form. We are simply substituting the Neumann boundary conditions here. Now we can rearrange these things and we get this equation. So the abstract form looks now something like this. So this is our AUU, u comma v, and this is our L. This complete thing for all v in phi. Okay, this is up to this point we have not talked about the approximation. This form is as strong as the differential equation. Okay, there is no approximation till this point. Now let us approximate this thing. Okay, so this is what we have developed till this point, and let's choose a trial solution, something like this. Since we have the Dirichlet boundary condition, that's why we are using a homogeneous for this Dirichlet boundary condition is homogeneous. That's why we need to use a boundary function bx, okay, whose value is a constant value 10 e to the power minus 4. This is because uh at 0 at x equals to 0, these functions will go to 0. That's why b0. Okay, this is actually b0. Doesn't matter because it's a constant function of x, so it doesn't matter whether we take it as a function or not. So for any value of x, it's constant. So b0 is also 10 e to the power minus 4. So that's why it satisfies the Dirichlet non-homogeneous boundary condition. Now the AUV part from here. Okay, this is our AUV, right? And for all v belonging to v, and LV, this part is this. Okay, now we substitute in this our approximate solution. We substitute this here, and we convert this single statement, one statement to n set of equations. Okay, by inputting psi i's in place of v. Okay, so AE u dash is b plus summation of cj psi j dash. Summation is implied over j, and from in place of v we have input psi I dash. Similarly, 10 in place of v here in the LV we have put psi I, and here psi I at L. Okay, now we can move this part. This is, since this is derivative of b is a constant, it goes out, and we get the term AE summation of cj psi j dash. Cj is also a constant, and psi I dash. We can take this summation out and cj out of this inner product. So this is the inner product now. Okay, so note that this is not the inner product. This is not an inner product, but this squares are inner product. These brackets are inner product. Sorry. Yeah. Now we can write this thing summed over j these are I equations. We can write this in this form, and we can solve this linear equation simply using Matlab or whatever. Okay, so where aij's are these terms, okay, which is nothing but the inner product of this term with this term, and bi are this, which is in which there is one inner product. This part is an inner product, so we have expanded it, and these two terms. Okay, so we started with this equation. We wrote the basic residual form, integrated it by part, and substituted the Dirichlet and the Neumann boundary condition, and we got to the abstract form of the equation, which is au v comma v is equals to lv, and we substituted the trial solution that we constructed into the weak form or the v form, and we did some manipulation to separate Cj, okay, and then we evaluated this aij and bi matrices so that we can solve this linear set of equations. So these are the results for different values of n when we have chosen the basis functions psi I is equals to x to the power I. Sorry for the writing. Okay, so we have chosen this type of basis functions in this case. Okay, so this blue line that you are seeing here, okay, that's the actual displacement solution, and these dotted ones are the solutions, approximate solutions that we get with n is equals to 1, n is equals to 2, and n is equals to 3. Okay, and this is our actual stress plot, which is nothing but E times u dash. So in some sense it is just the derivative of the u. Okay, that in this plot also we plotted for a different value of n, and this is how the error varies. In this plot we are showing that. Now some observations. Okay, so the C for n is equals to 1. Okay, the Neumann boundary condition was this, okay, because this is the exact solution. So this was the Neumann boundary condition that we had to specify, that we had to satisfy, but our n is equals to 1 case was not able to do so. Why this has happened? Because we have not constructed the boundary function for satisfying the Neumann boundary condition. That's why we are getting this error. But as we go on increasing n, we get closer and closer to satisfying this thing, okay, this boundary condition. Okay, and at n is equals to 3, we get the exact solution for both the stresses and the displacement. Okay, so this is the drawback of the weak form, that for if you are searching the solution in lower dimension, or for in FEM if the mesh size is too large. Okay, so in those cases you might not be able to satisfy the Neumann boundary condition exactly. Okay, this is one of the important fact about the weak forms. But but the thing is, you can approach the exact solution in which the Neumann boundary conditions are also satisfied in some average sense or in some approximate sense by increasing the dimension in which we are searching your solution. For example, in this thing, as we increased our dimension of the trial space from n equals to 1 to n equals to 3, we improved our approximation of the Neumann boundary condition. Okay, so in FEM we'll see that to satisfy these conditions, or to satisfy as best as we can, we usually go on discretizing or decreasing the mesh size. At this point, we don't know what mesh is and what discretization is, but if you come back and see this video, you will definitely understand what I am talking about. Okay, so this is how the result of the previous problem looks like. And also note that the Dirichlet boundary condition at this point is satisfied by all n's, okay, for the approximate solution corresponding to all the dimensions, because we constructed the boundary function to satisfy those. Okay, so at n is equal to 3, the error is completely 0. Now let us see how to implement this thing in Matlab. This is almost similar to what we have been doing. So this is the equation that we are solving. So we first define all the symbolic variables. We define what a naught x or e is. Okay, let us choose x as a function now for time being. Earlier in those results I choose x as a constant. So let us choose x as something like x squared. Okay, and e is the modulus of elasticity, which is 10e to the power 5, and the length is 2 of the bar. Okay, now the function that we have defined is fx is equal to 10 a naught into x. Okay, this is the area. What actually physically this is nothing but a distributed force, a body force acting on in the domain. This force is not acting on the boundary but inside the domain, like gravity or distributed load in the domain throughout the bar. Okay, and this is the value for the Dirichlet boundary condition, and this is the value for the Neumann boundary condition, which is nothing but EU dash at x equals to L. Okay, this is, now we have defined all the things for the ODE. Now we solve it using the symbolic function called dsolve. So we first define the ODE in something like this, which is nothing but since there is double derivative here, so differentiation of a naught e into differentiation of u, okay, with respect to x1, which is equals to minus f. So this is what our ODE is. We define the initial conditions. First one, we are differentiating the u because we want to specify the Neumann boundary condition. So these are the two conditions. One is Dirichlet, another one is Neumann. Okay, so this is condition 1 and condition 2. Okay, this is the Neumann boundary condition. Now we solve this ODE symbolically. Okay, this is the solution, actual solution of our ODE, and the stress solution looks something like this. Okay, now let us generate the basis functions by choosing a basis function of this type, and here we can select the dimensions. Okay, so similarly we constructing psi I and psi I d. These are symbolic functions again, and then we go on constructing the A and B matrix that we have calculated like this. Okay, so just writing this thing here, which is BS and AS. These are nothing but functions. These are not vectors or matrices. These are just symbolic functions. So in this part of the code, we convert it into A and B matrices or vectors by running it inside the loop from I is equals to 1 to n and j is equals to 1 to n, and assigning each element one by one. And then we solve this set of linear equations using this line of code, and then we try to plot the results. Before that, we need to generate construct of our stress, which is nothing but EU dash and U. The approximate solution for that, we need the psi and the psi dash, which we calculate here from the psi functions to regenerate various vectors that we could simply add. Using this operation, we can simply generate U over complete domain. Okay, so this is similar to what we have been doing. You can just go through the code and see what is happening. You can put the bookmarks and check what variables are there. So for example, in this variable PS, each row of this matrix PS is nothing but a specific basis function. For example, this is for psi 1 at x is equal to 0, at x equals to 1. X equals to 1 is what? This value of x in this vector is 0.202. So this value of psi, it is at x equal to 0.202. This is value of psi 2, which is x square, at 0.202, and so on. So each row is a basis function. Similarly for the psi PCD, which PSD, which is derivative of the basis function. Okay. So this is how we calculate our approximate solution stresses. D is nothing but our boundary function. Okay. So let us plot the results using this. In all of the previous examples also, I've been using this function called black fig, which actually converts everything into a black theme. Okay, now let us run this code first for n is equals to say 2. Let's see what happens. Oh, unable to find explicit solution. This ODE solver is not able to find the solution now. So what the problem is with this solution, this A naught, I guess. Again, we are not able to solve for that. Let us take constant A then. So it worked now. I think there is some limitation with this desolve, but we could have solved our method could have solved these equations. So this is not limitation to the weak form. This is Matlab's limitation of solving using this desolve. Okay, so these are our solution here: approximate solution, actual displacement, approximation. These are the actual stresses and the approximation. So this is the error, and as we go on reducing the size, say we go from this to say 4. Note that at n is equal to 3 we got the actual solution, so at this n is equal to 4 should also work fine. So that's what we get. Actual solution, exact solution is what we have achieved using n equals to 4 and this type of basis functions. Yeah, so that's it for this video. We have seen how to implement the weak form solution of weak form in Matlab for a simple analysis of a 1D bar. If you don't know what the analysis of 1D bar, you just consider the problem that we solved as a simple differential equation. Okay, so consider this as a simple differential equation, and we are solving it using the weighted residual method and converted into weak form, and then using approximation. Yeah, so that's it for this video, and in the next video what we are going to do, we are going to see the kind of summary of where we are, what we are doing, and we'll draw a simple flow chart, and we'll summarize what we have studied till this point, and we'll close this module with that last. Yeah, thank you for your time.